Hello everyone, in this video we will discuss the step 5 how to program the Beckhoff PID function block, that is a FB_control_PID, this function block. In the previous videos, we discussed how can we set up the TwinCAT3 project, how can we program the scale analog input and unscaled analog output. This video, step 5, that's our core of this series video. We will program the PID function block inside the TwinCAT3 project. From the step 1, I showed how can we download the PID Sample Program. Using this PID Sample Program, we can quickly build up the standard PID controller, FB Control PID. So let me show how can we do that. From the previous videos, we programmed the analog 2 channels, scale the analog 2 channels into these 2 global tags, and also we unscale this value, that is a 0 to 100 value, and unscale this value to analog channel. If you recall, those 2 lines for the analog output unscale, I demonstrate 2 scenarios. So in the practice, we will only use the 1 scenario by your application. So here I will comment the second line and only use the first equation. I will assume this channel, that is a 0 to 20 milliamp current channel. Alright, let's shift to the PID control programming. So if you recall, from the step 1, we open this sample 00, this program. And under this sample project, it has a program FB_control_PID. Inside this program, that is a typical PID controller. It has a basic structure here. It has a parameter initial and the instant PID controller, how it code this PID controller. So we can copy this FB_control_PID, this program, into our project. Okay, so from here, this is the sample project and this our new project. So I will copy this PID, paste to here. Before I paste, I will create one folder and named PID. Okay, I will paste this program here. Also, I will drag this PID_code under this PID folder. Okay, so this is the program we just copied. This is our main program to call all the PID program. So from this PID_code, this is the program coded by this cyclic task, that is 100 milliseconds. Okay, so from here I will call this PID program, program_FB control PID. Okay, this program will call this program. This comes from the sample PID program. Let's quickly review what the structure and what the detail within this program. This is our core instant PID controller. This is the instant name of this PID controller. And if we come here, we will see the instant name, this is FB_control_PID. The actual function block, that is FB_control_PID. And inside this PID, this is the setpoint value. This setpoint tag is declared at here. And this is the initial value is set 5. We can change it after. This is the actual process feedback value. And this actual value can be connected with the analog input scaled value. And the control signal, that is this, F-out. This control signal can be connected to the analog output. And this is the manual output direct, that is a 0 to 100. If we shift to the manual mode, so this F-out will be controlled by this manual directly. If the PID is working under the automatic mode, the output will be controlled by this PID algorithm. Okay, Another important that is this E mode. Look at this. This E mode, its actual structure come from this one, E control underscore mode. We need to find out detailed description from the website, from this help of the PID controller. Okay, other than this core PID function block, we go up. So firstly, this area can be comment out or can be deleted because it is used for demonstrate to toggle the settle point. Let me delete this. And the left things, that is this area, that is the initial. As we can see, the initial area will be initial this PID key parameters. This is the control cycle time. This is the task cycle time. Firstly, we need to change here. Since this PID program is coded by this program underscore PID underscore call, and this call is actually controlled by this cyclic task. This cyclic task, that is a 100 milliseconds cyclic task. So firstly, we need to change this task cyclic time. This one change to 100. This must be the same as this cyclic task. And this, the control cycle time, this time is used to control the actual sample time of the PID algorithm. For example, if you are going to control a temperature process, maybe the PID sample time could be 1 second or 500 milliseconds. If you are going to control a speed system, maybe the sample time of the PID algorithm must be a very quick sample time, for example, 100 milliseconds or 200 milliseconds. And keep in mind, this control cycle time must be greater or equal to this task time. And according to my case, because I'm going to control one temperature system, so my control time would be 500 milliseconds or 1000 milliseconds. I will temporarily type in 1000 milliseconds here. Okay. And these are the couple important PID parameters. We will temporarily leave those parameters here once we connect one actual process or the simulated controlled object. We need to tune those parameters. So we will leave those parameter template here. And this is our maximum output and the minimum output. Most of case, we will select 0 to 100. So I will set maximum, that is 100, and the minimum, that is 0. This is a float value. From all those parameters come from this structure, we will see ST control PID parameters. This tag follows the structure coming from library. Okay, and these parameters will be transferred to the PID, which is here. All those parameters will be organized as this structure transferred to the PID. Okay, and another important tag, that is this E mode. This E mode also comes from the system structure. So if we go up from here, we will find this E mode also comes from a control mode here. I will explain after. Another important tag for this PID, that is a process feedback and PID control signal. The feedback, that is this actual value. This actual value need to be connected with a scaled analog input. To connect this, we can go to the program code here. So before this program call, firstly, we need to transfer. For example, we will pick this analog input. We need to transfer this value to the PID actual value. We need to find out the full tag name of this tag. And let's go to the definition. And this is the internal tag of this program. So when we try to use this tag, the full name of this tag will be this: rg underscore fb underscore control underscore PID dot f actual tag. This is the full name of that value because this tag is a local tag within this program. Keep in mind this. And using this way, we transfer the actual analog results. This analog results come from the analog input scale equation, right? Transfer to this tag. And this tag will be transferred to the actual tag at here. All right. Then the output of the PID, that is this F out. This F out need to be used to transfer to the analog output. So come back here. Firstly, the same thing. To use that, press dot and this F out. This F out need to be transferred to this value. And then using this equation, this value will be transferred to the analog output. And this is the real value, right? So let's copy, paste here. All right, this is the actual PID output. And using this equation, we transfer to this value, and this value will be unscaled to the analog output channel. So through this way, we connect the input of the PID and the output of the PID. And then let's go back to the inside of this program. It still has some error here. It's showing here. Those tags comes from the global value from the sample program. So if we quickly review the sample program. So this is a sample program, and those tags come from the global value. So if we go to the sample program of this global tags, double click, we will find flow this. Those global variables are declared here. Okay, let me copy those declaration. Those tags will be used for the scope trained. It's very useful. So other than this, I also need to copy this out to scope. That out to scope. Okay, let me copy those three tags. This is my program. Okay, I will paste them to here. Keep in mind, those tags are long rail because all the PID rail, actually the rail that is a long rail. Okay, I will paste these three tags here. And these three tags flow here, they are the same. But it haven't finished yet. Kill here, let me build. It still shows the error. Even if we declare here. It seems very odd, right? Because from the sample program, it doesn't show any error here. I will explain why. That's because, firstly, all those tags, this tag, this tag, they all global variables. And if you find when this sample program try to use the global variables, it directly uses this name. However, in our program, when we try to use one global variables like this, it has a prefix name here. That's the GVL, if you remember. All the global value used in my program, I add this a prefix name. The reason why in the sample program, it doesn't matter, it doesn't use this prefix name, that's because in this global variable list, at the top of this variable list, one properties is deleted from this sample program. If I go back to my side, and this is my global variable list. If you see here, by default, it has a one attribute that named qualified only. If these tags are shown here, that means when we try to use this global tag, we must add this prefix. If you delete this, you can use this tag directly. You do not need to add this prefix. However, personally, I highly recommend you leave these attributes here. When you use this global tag, you better add this prefix name when you go through those programs. Because when you look at one tag, at a first glance, you don't know if this tag is a local tag or global tag, right? If you compare. But if you add a prefix here, GVL. So when you program like this, it's very clear for you to know, oh, those tags are global tag, and those tags without any prefix, they are local tag. It's very clear. Since in the TwinCAT3 project, we will mainly use the tag rather than the absolute address. So we better use the tag name to identify if this tag that is the local tag or global tag. Without this prefix, it's very easy to mess up if there's a tag that is a local or global. Personally, I highly recommend when you use a global tag, you better leave this default attribute here. And when you use a global tag, add this prefix. Okay, so for this global tag, I also need to add this here. As we know, there are three key values from the PID loop. They are set point, process value feedback, and the PID control output. So that's why from this code 23, 24, and 43, those three lines, we copy those three key values into three global values. Those three global values will be imported into the train. So using these three lines, we prepare those three key values into these three global values. So we can monitor those three tags or import into the train. Alright, that is the key program for this PID controller. Since we copy this program from the sample program, you can see it's very easy for us to fundamentally set up this PID controller. And the rest of things, that is connect the process value input and connect the PID output. It shows error here. Let's see what's going on for this. Oh, that's why. This F actual value inside this program, this F value, that is not input value. Okay, so we need to program that transfer inside this program. Okay, it's not a big deal. Let me copy this line, cut it, and go inside of this program, and paste here. So since this F actual value, that's the local tag within this program, so I will delete this prefix here, and this is the global value. We need to add this prefix. So this analog scaled value will transfer to this F actual value. This F actual value will be used to transfer this scope value, also need to be used as a feedback of this PID loop. And at the end of here, so let me go outside, copy this, cut, paste here. So we will transfer this F out to the global value, this GVL, this output setting. This setting, because this is a global value, so this global value will be used here to unscale, transfer to analog output. Okay, so this is the analog input, and this is the analog output. Till here, we still have two topics. One is this mode, what the detailed information within this mode, and one is this, what does means of those PID parameters. To check out this, let's go to the Beckhoff website, Infosys Beckhoff, and search FB_control_PID, and find out the detailed description of this PID controller. And this is the key equation of this PID controller. The key parameters of this PID equation, this is a KP, TN, TV. And this TD is a little bit special. And then let's scroll down, look at the detailed functional diagram. And take care of these two selection. By default, both of things, they are false. So this is the typical transfer function of this whole closed loop transfer function. This is a regular closed loop transfer function. But if you look at this, the feedback signal could be calculated with a KP and this Tn and the Tv. So with the different setting around here, the whole closed loop transfer function will not be the same. So it depends on what the selection. By default, look at this word. By default, both signals, they all false. So that is our regular closed loop transfer function. Okay. And then to check out the detailed description of this PID input and output, we can look at the detail at here. For example, the side point, that is the side point of the controlled variable, and feedback, that is the actual value. And for this manual synchronized value, when the PID is working under the manual mode, so we can set this value direct control the PID output control. That value, that is 0 to 100. And for the mode, we can click this link to check out the mode. And a couple important parameters, you better read the detail. This is this control cycle time and the task cycle time. Also, this parameters, for example, Tn, that is the integration action time, and the Tv, that is the derivative action time, and Td, that is a damping time. Regarding this TD in the Beckhoff PID algorithm, if we compare the same PID algorithm from the Siemens TI Portal PID compact, the same spot, this TD named derivative delay coefficient. The only different that is this coefficient in the TI Portal, that is a small a times the TD. That TD, that is the derivative action time. So usually this coefficient value, it could be set at 0.5 or greater than 1. You can look at the detailed description here. Okay. And let's click this operation mode. Click. And it's jumped here. And this is the E_control_ mode. So this list is very important. Basically, we will use this manual mode and the active mode, that is the auto mode, and this is the manual mode. So we'd better copy this, paste to our program, and paste there as a comment. For example, we could paste here, and firstly we can comment this out. So those values could be used as a reference when we try to control the PID loop to a manual. We can set value 4 to this E mode value. This value. Okay. If we switch to the PID to automatic mode, we can set a 2 to this value. This is the mode is very important. Alright, that is the offline program for this PID controller. And in next video, I will show how can we use one second order transfer function as our controlled object. And this controlled object will be connected to this feedback actual value. And this PID control signal will be connected to this controlled object. And use this simulated object as our controlled object. And build up this whole control loop. And after that, we can download this whole project and do the online test. Alright, that is it today. Thank you for watching. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.